Yeah, before we start, perhaps the door should be closed.
Okay. You're welcome. Hello, my name is Iypt from Team USA, and I will be presenting the looping pendulum. So the looping pendulum is essentially what we have here. So we have a heavy weight attached to a string, which is attached to a lighter weight. We release the lighter weight, and it swings around the rod and holds itself fast. So to begin building a mathematical model of this phenomena, we will start with a simpler version, which is known as the swinging Iypt machine. Essentially, this is the looping pendulum, neglecting friction and drag forces and assuming a dimensionless rod. To find the equations for motion of the swinging Iypt machine, we set up a Lagrangian like such. We have kinetic energy and potential energy, and subtract the two to get the Lagrangian of the system. We use Euler-Lagrange's equation to find two second-order coupled differential equations for the motion of the light mass. Here's an animated GIF of the motion of the lighter mass. As you can see, the beginning motion follows the same trajectory we see with the looping pendulum, but over time it becomes a chaotic system. Here's another graph of the swinging Iypt machine. We stopped generating the graph when the radial velocity was 0 to simulate when the heavier mass stops moving. To include air resistance, we use Rayleigh dissipative forces. So F is a Rayleigh dissipative function in units of energy associated with drag from air resistance in this example. So we have the function for air resistance here. K is the constant. And so we use this with our updated Euler-Lagrange formula to get two new second-order differential equations. As you can see here, here is the air resistance. To solve for the constant K, we built a wind tunnel. Essentially, we have a fan blowing air through this tunnel. We have an anemometer here to measure the wind velocity. And we have the lighter mass attached to a string to the ceiling. Here's a picture of our wind tunnel. So as you can see here, here's the anemometer measuring our wind velocity. So to solve for the constant K, we have a force diagram here with the drag force like such. We can measure the angle that the string makes with the ceiling using this slit here and a ruler. We measure the change in the position of the string and trigonometry to determine the angle it makes with the ceiling. So here we plot using a number of wind velocities to determine the constant K. We expect a constant between 0.47 and 1.07 according to NASA, and our calculated coefficient for drag is 0.821. We graph air resistance, and we notice negligible change from the graph without air resistance. To include friction in our system, we will derive an equation for friction between the string and the rod. So we define d theta to be the amount of angle wrapped by a small chunk of the string, or d phi, I'm sorry. We set up a force diagram on this small chunk of string to determine equations for the normal force and frictional force as functions of the tension in either side of the string, the hold and the load. We then solve for the tensions load and hold. So the tension of the load, we include gravity and acceleration. Here with the load, we have just gravity. So hold has additional centripetal acceleration. Here, we then plug those into our formulas for normal and friction. We plug in hold and load to determine these new equations. We know that the coefficient for friction is equal to the frictional force divided by the normal force. So now we have this large equation that's equal to the frictional coefficient. We then set up this experiment here, where the radial acceleration is equal to 0, the angular velocity is equal to 0, and the angle wrapped around the rod is exactly pi radians. So here we see we have a simpler equation for mu using this experiment. We ran the experiment a number of times with different mass ratios, and we got the following best fit line, which has a slope of 0.208. So we know that the frictional coefficient should be 0.208 approximately. Finally, we used the modified Euler-Lagrange equation that we showed earlier with our new mu, which is right here, to obtain the following large second-order coupled differential equations. However, we have one more thing to account for, and that's the thickness of the rod. So to account for the thickness of the rod, when we run our second order differential equations through MATLAB, which is our coding software, we use the Euler method to solve these equations. And at every time interval, we take out a chunk of radius equal to L times d theta, as you can see here. So basically, for every small time chunk, we're taking out L d theta, which is the length of this pink string here. So now we test our model. So we built the following rig to compare our results to our mathematical predictions. So here we have a tart to obtain good video footage. We have a number of rods to stabilize the rod that our looping pendulum is going around to minimize wobbling. We also have a magnet here that can be released mechanically to prevent any human error in releasing the actual weight. We use a program called Tracker to track the position of the lighter mass at every time step. So here you can see each one of these dots represents the ball's position on a single frame of slow motion video footage. So here we've graphed the tracker, which is these blue dots. The tracker is the actual position of the ball. The red line represents our mathematical simulation of the predicted ball's motion. Here, the green dot represents where we think that the ball should have locked in place, or the rod should have locked in place. Sorry, the string around the rod. Here is the blue is where the string actually locked in place due to friction. We determine these positions by looking at the heavier mass and noticing when it stops descending. Here's another example. In the previous, in this model, or in this trial, I should say, we used a high stretch thread, which was made out of some sort of material such as cotton or thread. In this example, we used a fishing line because we realized that it has a lower stretch, and we noticed that it becomes much closer to our actual results. Particularly, you notice that the predicted lock-in position is very close to the actual lock-in position, and the entire graph is generally tighter. So examining the stretch of the string, this is a graph of the y value of the heavier mass as a function of time. So as you can see with the high stretch thread, the mass actually bounces significantly at the bottom. This is the heavier mass. Whereas with the low stretch fishing line, it barely bounces at all, leading us to believe that if we could have a minimal stretch line, our mathematical model should line up nearly perfectly. Here we graph the conditions for failure. So in this example, the light mass does not have enough gravitational potential energy to actually swing around the rod. And so in this case, it collapses and does not make it around, and we see that our model is even able to match up with a failure condition fairly successfully. Here we have a minimum successful ratio. So basically, we configured our starting conditions to make it so the lighter mass collides with the rod. And again, we can see that the mathematical model lines up fairly well. At this point, the string becomes slack and our model no longer functions. Here's an interesting example. You can see that the lighter mass comes to a complete stop here, and then actually after a little bit will begin dropping again, and then come to a second complete stop. In this example, our model stopped here because here was the first complete stop, but nonetheless it is interesting to see that it's able to match up at least until that point. So anyway, in conclusion, to summarize, we created a mathematical model using Lagrangian mechanics. We started with the swinging outwards machine, which is a simpler system. We introduced air resistance by using Rayleigh dissipative functions. We solved for the coefficient of air resistance using a wind tunnel. We then incorporated and solved for friction. We derived an equation for friction between a string and the rod. We then incorporated friction into our equation. And then we included the rod's thickness by incorporating it into our Euler method when we solved the differential equations. And then we tested this in a number of trials with a number of different conditions, including failure conditions such as the one right here, and showed that we have fairly good matchup. We then explored the effects of stretch of the string and noticed that the less stretch that was in the string and the less spring energy was being contained in the spring, the closer our model lined up with reality. And we hoped that if we could have a minimally stretched string, if such a string existed, then we would be able to line up nearly perfectly. And finally, here are some references that we used for our work, especially with the swinging outwards machine.
Okay, next, please. may depend on some relevant parameters such as weight ratio or the angle or something like that.
Yes, so what we noticed is, for example, with the weight ratio, we needed a sufficiently high weight ratio in our failure condition. The main way that we actually made it fail is by making the heavier mass much lighter. As you can see, those are much smaller masses. So that's one example of how you can make this fail. And with angle, like you said, if you make it a shallow enough angle, there's not enough gravitational potential energy in the system to allow the lighter mass to go all the way over the ROUND.
How do you think that if the light one angles around just a little bit, it would fall anyway?
Yes, we've noticed there's actually an equation for this called the capstan equation. If the following equation is not true and the hold is not, there's not enough tension in the string, in fact, the friction force will not be able to hold the mass together and it will slip off even after it's finished wrapping.
Okay, how many angles do you think it needs to actually stay and
Typically, it's about 3 or 4. As you can see, with the number of wraps is represented by theta, which is the angle wrapped in radians. And as you can see, the tension or the frictional force increases exponentially as a function of angle.
Okay, thank you.
Do you have any further questions?
That's all, thanks.
That's all. Thank you, and now have your clock is already running, so.
Okay. So we heard about the problem number 14, looping pendulum from USA. I would like to summarize the board's presentation. I like the theoretical description. It was their own theory from Lagrange equation and others developed. They also measured the air drag and friction from fit experimentally. They also had a good setup. They've shown us how it works. Also, I think that the experiments could be a bit better in terms of how the relevant parameters and what's actually happening. We like the theoretical model, the correlation, that was really nice, but we think that the experiments could fulfill it a bit better. Points to discuss. I would like to discuss the behavior after stop and also the experiments.
So is that all?
Yeah.
Then let's thank the opponent for the opposition. And we can now proceed to the discussion in which the reporter and respond to critical remarks from the opponent.
Okay. So let's start with the behavior after stop.
Next, please.
Do you think you can simulate this? Because I think it might be a little bit easier than the whole thing.
Absolutely. If I may go to apologies. Here it is. So the motion after friction takes over. Essentially, what happens is we have 2 new constraints. There's no radial acceleration, or at least in the heavy mass, and there's no new radial velocity, or radial velocity is constant here. So essentially, what's happening is we have the following, where basically, because there's no change in radius, it generates an Archimedean spiral inwards. Or the heavy mass is not changing. So we have this constant inward spiral with a constant radial velocity inwards, which generates, like I said, an Archimedean spiral.
Okay, and do you think that you could theoretically simulate this, and as you said that you have double stops, you can simulate that as well?
Certainly. All you need to simulate the double drop is after the first stop, you would just need to restart the simulation in MATLAB. to follow the motion until it has a second stop, and after the second stop, once everything is completely taken over by friction, then all you have to do is set it into Archimedean spiral mode, and then have it draw an Archimedean spiral inward from there.
Okay. What do you think about the parameters that are relevant? Do you think that you could do more experiments about that or something like that?
Certainly, the relevant parameters we found are the mass ratio is a large one, the angle made, the height of your light mass. All of those are very relevant. We did not feel that the problem statement required us to find exact numerical values for the thresholds for these phenomena because they're all interrelated, and finding such would be incredibly time-consuming and tedious. However, it's certainly possible if I had enough time to run the experiments that I could find values for this.
But if you think that it's not, the task is not about those parameters?
No, how we interpreted the problem is to mean that we can generate a mathematical model that will model the motion for any given starting conditions.
Okay, that works quite well. Do you think that you could use the Capstan equation inside your theory because you did your kind of own friction?
Yes, so the difference between the Capstan equation, which is here, and my derivation for friction is that this is only valid for static friction, whereas mine is functional for kinetic friction. The issue with static friction versus kinetic friction is static friction has an exponential. The frictional force is relative to the exponential, whereas the kinetic friction force, as you can see here, is proportional to many other things, but no exponential is to be found. This is simply a result in the Capstan equation of how the integral is set up to solve it. In this example, we're integrating where the force of friction, if we go back to which slide do I want? This one. So essentially what's happening is with static friction, we have to deal with the fact that the hold and the load are unchanging, which changes our frictional, both equations for friction and normal significantly, and thus our equation for mu.
Okay. So did you change the weight ratio also?
Yes.
So do you think that if I would change it to infinity, like that the light one would have a mass around 0, would it make a change?
If you were to create it infinitely, it's possible, or if you were to make the lightweight infinitesimally small, it's possible that there would be no slack, or you would not be able to have any sort of tension in this rod. And in that case, because the rod is slack, the model would not be able to handle such a scenario. If you made the light mass a normal value and the heavy mass infinitely large, essentially what would happen here is this mass would be pulled almost directly inward because of, and it most likely would not be able to, would either not be able to make it around because it collides with the rod, or wrap around very quickly.
So what do you think is the outcome of this stuff for you? You got the models, and is that things?
In my example, I was very satisfied with our model because of its ability to predict not only the success conditions, but also the failure conditions significantly well. If I was to revise anything, I would probably want to attempt to incorporate the stretch of the string into the problem. However, I did not feel that the stretch of the string was necessarily part of the problem statement. It merely wanted the motion, and I felt like the assumption here is that strings should not stretch. And so we attempted to minimize the stretch experimentally rather than theoretically.
Thank you.
Is that all?
Can you tell us what was the how was the experiment for measuring the air drag?
Oh, the experiment for the air drag?
Yeah, some equations.
Yes. Okay. So if we go back to the initial, so whenever we have a non-conservative force, such as air resistance, we have to use this modified Euler-Lagrange equation, which includes Rayleigh dissipative forces. So to model air resistance as a Rayleigh dissipative function, we make it proportional to the square. That way, once we are done integrating, it'll be proportional to, rather than the square. We have a linear proportion. And so to actually determine the coefficient for drag, if that's probably what you're considering, we have this wind tunnel here. We have a known wind velocity, and we have we set up the following force diagram. So knowing that in the stable state, all forces will equal to 0 because acceleration is 0, we can use simple vector addition to isolate the drag force in terms of the angle and the gravitational constant and mass. We can measure the distance that the string moves forward to determine the angle that it makes with the ceiling, having a known height between this and the ceiling, simple trigonometry. And then we plotted it using a number of wind speeds and then measured drag forces based on the angle that we received. And then finding a best fit curve through this, which in this case is going to be a parabola since it's proportional to the square in the drag force in the Rayleigh dissipative function, thank you. Because it's proportional to the square, we find a best fit parabola, which gives us a calculated drag coefficient of about 0.821.
What object do you use as a light weight?
Yeah.
Because I wonder if that could spin somehow and change the airbag a little bit.
I'm not sure if I have a picture of it besides when we actually let it go, but essentially what we used in our experiments was we colored a magnetic ball green, and so we used this lightly consistently, and because the experiment is only varies based on the mass ratio and not the individual masses, we only vary the heavy mass and leave this mass constant so that its air resistance is consistent.
So it's symmetrical in all axes. It's spherical, right?
Yes.
Okay. Do you think that the loads can hit each other? So you have the kind of misdirection a bit?
Yes, so we definitely had experiments where either the weights collided or the lighter mass collided with the string. So simply what we did not want to offset it in the z-axis because we felt that would skew our results. So we essentially just attempted to continue dropping it until we happened to get a trial that did not collide with the string.
Okay. So you kind of...
About 75% of our trials did collide with the string, unfortunately.
Yeah, so you negated the more experiments than
Yes.
just...
Yes.
Okay, that's all.
Thank you.
That's all? Okay. Is that all? Ronan? That's all. Okay. Let's thank the reporter and the opponent for the discussion. And now, attention please. We have 1 minute to summarize the discussion, which is done by the opponent.
So first we discussed the equation and simulations after the first stop. Then the reporter said that we have to start the program again. I think that would be some technique done another way. Then we discussed the parameters with the different mass ratios, but the reporter wasn't able to make simulations for every parameter because it would take a lot of time. Then we talked about the Kaplan equation compared for measurement in static and dynamic form. Then we also asked for changing the weight ratios into infinitely. Also, we discussed the outcome of the task. Last thing, we've discussed the measurement of air drag. I think that the discussion was really productive.
Okay? Thank you very much.
For both the opponent and the reporter, why do you think the heavy load will stop?
The heavy load stops essentially when the frictional force becomes greater than all of
So
the
it's
force of
frictional
gravity.
force caused the heavy load to stop, right?
Yes.
Then opponent agree with the reporter. Like why will the heavy load stop?
Yeah, because of the frictional force. As
Okay,
I asked with the
okay, thank
equation,
you.
how many times it times.
Thank you. Then what is the reason you investigate the stopping position of the light load instead of the dropping distance of the heavy load?
Those are essentially the same things. How we investigated the stop position of the light load was basically the stop position of the heavy load. We just marked the position of the light load when the heavy load stopped.
Okay, thank you. Then you mentioned that there will be phenomena like drop again, right?
Yes.
Then why will it drop again?
This occurs, I believe I talked about the capstan equation. So the capstan equation is valid for static frictional forces. When that equation does not hold because there's not enough static friction, it'll drop again and resume the motion until the static friction is.
Then is there any condition that will make it drop again? Will have a range of mass ratio?
Yes, so the conditions that we found is all we have to do is find a mass ratio that's close enough that it does not stop immediately,
So
but
if the
not.
mass ratio is small, there will be drop again phenomenon?
If the mass ratio is too small, then you won't get it to drop again. But if it's too large, it'll simply fall off and not stick a second time. So you have to find
a range of
there's a very narrow range of mass ratios that will work.
Do you have the volume of it, the range?
Unfortunately, the range varies depending on our starting angle and height. So finding those values both theoretically and fundamentally would be too challenging and time consuming.
So we don't have it, right? Okay. Then then you measured the friction. Did you consider that there will be phenomena like the string will rotate on the string? Opponent, do you think there will be phenomena like this?
Yeah, I think you cannot control it.
Then the opponent did not consider, well, do you think that matters
Yeah, maybe that might matter.
a lot? Is that negligible or not?
But I think that might depend. The phenomenon might depend a lot on this. If the angles are around the road.
Okay.
Yeah.
Then do you think the stopping position will change if we change the total length of the string?
So the total length of the string does not necessarily matter. It's only the length of the string of the lighter mass because.
So will that like change or not? Stopping position of the light load?
If you change the string of the light mass, yes.
Really sorry, yes, but we're out of time. Thank you for your questions, and now we have your preparation time.
Good afternoon, everyone. I'm the reviewer from Team Taiwan, and today I'll be reviewing problem number 14, looping pendulum. Here's the problem statement. The main focus will be on what causes the phenomenon to happen and how the parameters going to influence the phenomenon. And here's the performance of the reporter. In the phenomenon part, he gave us a observation video which shows the clear phenomenon, but there's no qualitative explanation on it. And the physical meaning, in the theory part, he told us about the outlet machine, the Euro-Lagrangian theory, and the friction and air drag calculation, which I think he did a good job on wind tunnel to solve for K, but the physical meaning of equation not well explained, and the motion to model calculation did not well explained. And in the experiment part, he told us about the motion, but in the elasticity part, he only did the experiment by, instead of giving explanation on it and the mass ratio, the failure, and the double drop of the phenomenon. And he did go on look into the failure and double drop and finally a conclusion. And here's the opponent's pros and cons. The opponent presentation, he didn't give other relevant parameter to be discussed, and he could have used time more efficiently in discussion. And in the opponent did a good job on bring up lack of relevant parameter of the reporter, and the cons is that he has little assessment of the reporter and few values and few block points of discussion and only ask questions. And here's the discussion on motion after heavy load stop. The opponent only asked questions on it and without giving any own contribution, the reporter answered the constant radial velocity. But I think that the light will accelerate because angular momentum must be conserved, so velocity not constant. And as for friction part, the opponent asked question to the reporter, and the reporter said that he used capstan question but only for static friction. I think that we can use capstan question for kinetic friction as well by including the acceleration of the string. And as for elasticity part, the opponent said that it will affect, but doesn't say how. And the report ends by replying that this is not important. But I think that the length of string will oscillate, so the trajectory will be different, and that might cause a mismatch in reporter's graph. And they also discuss the resistance and the collision between the rods. And here's the appointments on during the discussion, which they did not talk about the friction part, which when the head load drop, the friction will be kinetic friction, but when head load stop, the light load spiral on the horizontal rod, there will be static friction. So they did not fully discuss on the friction, which is very important part in the problem. And the limits of theory, the reporter did not give assumption on it. And the length of string as a very important parameter that after you change the length of string, the dropping distance of the head load will be different, and the boundary of different phases occurs as I ask for the threshold. And we can investigate on other variables like dropping distance of head load and acceleration load, and the mass ratio of head load when we have same mass ratio but different component of it. And thank you. This is the end of my presentation.
Thank you for your review.
Thank you for the review and opposition. In conclusion, we built a mathematical model based on Lagrangian mechanics and other well-known phenomena. We generated formulas for air resistance and friction. We investigated the effects of elasticity experimentally. To address some of the points in the opposition, we talked about the motion after the static friction takes over. We discussed that this is in fact an Archimedean spiral, where the function is the radius is equal to the angle swept. It follows that sort of path inward. We talked about the phenomena itself and how we could, the parameters of the phenomena. We explored the mass ratio. We discussed the mass ratio, angle, and height are all various parameters that are all dependent on each other to determine whether the motion will fail or stop. And because these are all interdependent, how it would be very difficult to obtain these both theoretically and experimentally. We also talked about, and then to conclude about the motion itself, a qualitative explanation. Because this is all founded in Lagrangian mechanics, we have the beautiful principle of least action to govern all of this motion. So essentially, when we have the kinetic energy, the translated gravitational potential energy in the heavy load, all being translated into kinetic energy in this light load, we know that because of the principle of least action, the lighter load will have enough energy to get over the rock, and additionally will follow the path shown in our mathematical model.
That's all. Okay, thank you. John, please.
So you started out by looking at a system involving two rods.
Yes, the two rods should not matter.
Can you
because
just clarify how that was relevant to the problem?
it doesn't matter whether there's two rods or not. I could move this string over here. In reality, the two rods is just to make this system more clear. The rods are dimensionless, and the actual position of the two balls relative to each other is irrelevant, because gravitational potential energy is only based on the change in height and not any initial
Thank you.
height values.
Okay, Clara, please.
How do you, are you sure that there's no slipping, especially the first part of the beginning of the looping?
There is lots of slipping, and that's why we account for it in our derivation of friction. In our friction derivation, we use kinetic friction, which allows us to account for the slippage. Now, once the heavy load stops moving, we can be guaranteed that there's no slipping. Otherwise, the heavy load would continue to go downwards. Once we know that the heavy load has stopped going downwards using our tracker software, we know that the motion has now been converted entirely into the Archimedean spiral that I discussed.
How does a slipping associate with the new friction?
What do you mean? I'm sorry, can you
If you
clarify
think
the
that
question?
friction is a kinetic friction and it's a slipping,
Yes,
then-
I agree.
then how do you relate your slipping to the friction? How do you know how much slipping there are?
Simply by looking at this mass here. We know the coefficient of friction, and so using the principle of least action in Lagrangian mechanics, we know that there is one and only one path that the light mass will take given our initial conditions and coefficient of friction. we can note the slipping experimentally as well by looking at the position of the heavy mass.
Okay, Daniel, please.
I have one question to the reviewer, please.
Say again?
You mentioned that there is that kind of stopping of the bigger mass, and then it begins to slip again and stops again. Do you have kind of an easy qualitative explanation why this happens?
As the reporter already mentioned, that when the heavy load stops, then the heavy load stops, but the light load will rotate to this place. Then rotate to this place. Then the light load will have enough like potential energy to hold the heavy load. So the heavy load will drop again, but the light load will swing to. Have the light load then continue to swing to this place, then it will have enough frictional force to stop the heavy load again.
Okay, yes, Daniel, please.
Another question to the reporter. As far as I could see, you only tracked until the heavy mass stopped, and never tracked it to the real end. Or do you have?
We tracked the ball using video footage after the heavy load stopped. Our simulation stops once the heavy load stops because the differential equations no longer function because static friction has taken over kinetic
I
friction.
agree with that, but did you try to like go on with your modeling and then compare it with a tracking to the real end?
We didn't feel that was necessary since simple geometry guarantees that the motion would have to be an Archimedean spiral if there's no slipping.
Okay. To the opponent, do you agree with that statement?
I would have done that, but
Okay, thank you.
I think that the model fits it in that way, so there's no reason that it would not fit it in the next graph.
Okay, to the reporter, please. Can you show the slide where you had the trajectory tracked by your software? It had error bars along both axes. I want to check what these error bars actually mean. Yes,
These.
here they are. Yes.
The error bars represent the width of the ball. We allowed our tracking program error enough. It's supposed to detect the center of our ball as it's going. However, we allowed it error enough to detect any point on the ball. So those error bars are the radius of the ball.
Okay, can you say a few words about the reproducibility of your measurements? If you repeat the same experiment again in similar conditions, would you get a similar trajectory, or it would be different?
I mean, as similar as we can. Obviously, the simulation would be the exact same, but the trajectory, because we're using a mechanical release, and the rod, we have the whole rod set up to make sure that there's no movement in the rod or the release. We're getting almost the exact same motion every time with the same initial conditions.
Okay, we have time for one last question, if you have any. A very short. Okay, Francis, got a quick question.
A short question. In your simulation, it is clear that it differs slightly from the experiment. What do you think is the main reason? Which parameter should be changed?
The main reason is because of the stretch of the thread. As we said, this is a graph of a high stretch thread, which is made of string. And in this example, we use a lower stretch fishing line, which makes the entire motion match up much smoothly, especially the lock position.
Okay, thank you for the answers and thank you for the questions. Okay, so I will just look here. Okay, reviewer. Okay. Okay. So my score sheet is filled and signed. I have my grades and signature. Yours is filled and signed. Just show it to me. Yes, you have your grades. I just need to check that we have the grades. If it's empty, so the jurors show their grades, then we have a problem. Yes, it's not empty. Okay, good. Now we can start announcing the grades and the order from me. Yes, and František will be the last. And first we start with the grades for the report. The grades for the report are as follows: 6, 7, 6, 5, and 6. Thank you. Next we have the grades for the opposition. And these grades are as follows: 4, 4, one more time 4, again 4, and one more time 4.
Wow.
And next we have the grades for the review. These grades are as follows: 6, 7, 7, 5, and 8. Let's thank the viewers for the grades.
Really appreciate that you observe the whole trajectory towards the end and try to just change the model the way it calculates everything to the real end. Because as you see that you have like mismatching results, then it might even get worse towards the end, and that might show you that not everything is done really properly. So I don't agree in this part. And what I would have appreciated is that you really go deeper into the subject, like the tedious work that has to be done, and then it goes into the direction of creating a phase diagram, and really pointing out in which mass ratio, how does the system behave. So that was
At the opposite end of the spectrum, we had the single highest grade of 7 from John for the report.
Yeah, well, let's be clear about this. There are 7 points available for the report this year for the first time. So my scores were pretty consistently 4 out of 7 for the aspects of the report, which is not a massive score. And then for the discussion, I just think that the reporter handled what came from the opponent really with just total confidence, and just delivered your responses with beautiful timing. I just like that you weren't fazed by any question. I just loved the way that you said, yeah, okay, fair enough, and you gave your answer. So I thought it was a super discussion from the reporter's point of view. So that picked up another 2, and that adds up to 7, with no marks deducted from the jury.
Okay. If we look at the grades for the opposition, there was a very narrow distribution. In fact, we all gave the same grade, the grade of 4. So probably someone would like to comment on the grade of 4. Yes, Daniel, please.
for me again, it's rounded down from 4.5, and I felt that you tried to go into that mass ratio, and I would have loved you talking about the phase diagram I've already mentioned. So you were not really able to attack it in a better way, and I wanted you to point out more these deviations and really go into that stuff in detail.
I'd
Okay,
like to add on
yes,
to
please.
that. Yeah, I think that the critical part from the opponent was like almost every part they only use like a half of the time, and that's I think a big minus.
Okay,
Yes,
František?
Yeah, thank you. I would have mentioned this too.
Yeah.
Yes. If we look at the grades for the review, the single lowest was 5 from Daniel.
Yeah, that again is rounded down, so I could have given 6 too. Here I loved actually the part with the missed physics, that was great. On the other hand, that everything that came before wasn't in a really good structure, so it was like, you know, I want to be more precise there, and I couldn't really get the points. You mentioned things, but I wasn't sure whether you really do it the right way around. There was once you mentioned that centrifugal idea was interpreted the wrong way, so you should really try to give more explanation why you feel so.
Okay.
Okay.
At the opposite end of the spectrum, we have 8 from
I was
František.
quite happy with the review. What I mostly like, besides the miss points part, I liked that you show us your opinion to many things which were mentioned during the discussion and during the presentation. So I was especially like your expression of your opinion, what they claimed and what do you think is true, is not. So I can read it to you partial grade, but I ended finally at 8.
Okay. Do you have any questions about any of the remaining grades? If not, then thank you very much for being with us at the stage 1 of Physics Fight 1 in Group H. And now we have a coffee break. Thank you.